program would run on thousands of different models of computers. So if you think about that, back then there wasn't a lot of standardization. That means his program would have to take into account whatever hardware it was running on, and it would have to initialize things such that someone could actually use that hardware towards some meaningful purpose. And we can debate about whether or not 1980s computing was meaningful. I think it was. So his program was broken up, roughly speaking, into three parts: the BIOS, basic input operating system, the BDOS, or disk operating system, and then the console. And some of you here might recognize that DOS acronym. For me, it was the first way that I learned how to break a computer. But unfortunately, the reason you might not have heard of Gary is because he was in the mid-80s overtaken by a different company. And you might recognize that company. And we're going to talk briefly about this. But while I talk about it, I figured you might not want to stare at that picture, so I'm going to do something a little more nice to look at. So Microsoft took over, and the real key that I want to get across here, we're talking about DOS and the transition to Microsoft really owning the home PC market as they did for so long, is that the idea of standardization. In the 1980s, there was not a lot of standardization, neither from hardware or from software. Everything was essentially roll your own. And for those of you who were in the industry before that, I'm sure you're thinking, well, it was pretty standardized. As we know computers today, it was not. It was very much unstandardized, and there was a lot of work done by the industry. And by the industry, I mean people like my employer, to try and standardize things. Because at the end of the day, people needed to sell products. And you can't sell products quickly if everything is roll your own. You have to start creating abstractions. So you have, the first thing that you have to abstract out, and for argument's sake, let's say it's what BIOS was trying to do, trying to abstract out the hardware. And the reason it was doing that was because there was a huge proliferation of lots of different computers. Not just one kind. You could buy a lot of different kinds, and they all had their own interfaces, they all had their own software running on it. It was one of those worlds that was ripe for standardization, so that people could start actually selling products at a scale. And one of the ways they did that was with BIOS, and the idea being that this firmware is going to live on some piece of memory. It's going to be the first thing that's run. So it's going to abstract out that hardware idea and present something to the operating system. So if the operating system is written such that it knows what it's going to be interacting with, it doesn't have to care what machine it's on. It can run on any machine. So this was sort of the first level of abstraction. And the thing I'd like to call out here is that there was really just one chip on the screen right now. And I chose one that's erasable with UV light, because to me that's just an amazing thing that happened. This was the first level of abstraction, and it really came down to one chunk of software that people would consider BIOS. So just one thing that was going on that was abstracting everything. What happened then was the 1990s. And we started to approach an era where now one abstraction wasn't enough. The 1990s brought a lot of changes. There are two that I'm going to focus on. The main one is that BIOS became more configurable. So before the BIOS configuration utility, you basically had to change a bunch of diff switches on your computer if you wanted to change the way the computer acted before it booted. The BIOS configuration utility was the first thing that introduced this idea that, hey, what if we could configure our computers interactively as soon as they start, before the operating system gets loaded? And that was a new concept, I mean, relatively new, especially for the home PC. And it led to what firmware is today, that idea of configuration. Because for any of you who have worked on a software project, think about making a piece of software configurable, and then think about what happens if you then keep growing that software over the course of the next 2 decades. It's going to get extremely complicated, because as customers come up and say, hey, it would be awesome if it did this, they bake that in. And then when they realize they need to upgrade this piece of software, it's become a giant beast. And upgrading becomes now a multi-corporation endeavor to try and standardize this new thing that you're into. The other major thing that happened that I'm really just going to touch on briefly, because it is its own talk, is the introduction of microcode. And the introduction of microcode really just, to me, that shows you that microprocessors are getting extremely complex now, to the point where we need microcode. The uses for microcode, like I said, if you're really interested in microcode, I highly recommend looking at this paper called Reverse Engineering x86 Processor Microcode. I will leave these slides available online as well, so you can look up all the small text. But I'm going to go over just a couple of things that microcode does so that this is the bullet point I use when I'm out in the field and someone asks me about microcode. I pull out these 4 bullet points. The first one is complex instruction set encoding. How many people in this room have programmed in assembly? Yay! Oh wow, boy am I in the right room. Okay, so I programmed in MIPS assembly. It turns out it gets more complicated than MIPS. So for example, vector floating point arithmetic is not something I know how to do in MIPS assembly, but evidently it's a thing that can happen. And the complexity of that calls for another set of instructions that can be translated into the machine instructions that are more simple. The other one is fixing CPU bugs in the field. So this, you'll see, this is sort of an overarching goal of firmware, is when the hardware engineers are done, it's going to be really expensive to re-spin those 2 million parts that you just spun. So it's much easier to just fix that in firmware. Or in this case, if it's low enough, in microcode. And we all know that never ever happens. Exception handling is another one. So things like division by 0, when you have architectural level exception handling. And then finally, power management. Again, this is something that you can go look up that paper on. There's been a couple of talks on it too. It's a really great resource. Oh, sorry, one more. Advanced features. Almost forgot. So for those of you who want to throw tomatoes at me about Intel software card expansions, feel free to. It's not my fault, but I'll take the tomatoes because I'm dying. So things like secure enclaves can be implemented. Last part about microcode that I'll talk about is the fact that it actually lives in silicon, so in SRAM. So it's going to live somewhere on the thing that Intel is spinning, and I cannot tell you exactly where because my floor plan knowledge is not that good. But this is kind of the transition point from microcode over to firmware, because if this is where microcode lives, then firmware lives on this board somewhere. It's going to live on ROM. And what I'd like you to take away from this talk is that it lives at a certain place on some ROM chip, and it probably lives on several different ROM chips that talk to several different processors. So firmware doesn't just interact with the CPU, it actually interacts with a lot of different things. So for example, how many of you in here know what a board management controller is? Oh, good. Board management controller, a lot of you don't know. So believe it or not, if you buy a Xeon-based server, you're probably getting an ARM chip made by ASPI on there. And it's running an embedded Linux distribution called OpenBMC, I hope. The basic idea is that we want to be able to control these computers from a room somewhere else, and we want to be able to interact with them whether or not they're turned on. So you turn your computer off, but it can talk to the BMC. So you've got firmware running on an ARM-based system, embedded system, on your x86 dual Xeon server. So if you're not scared about firmware yet, now you should be. This is the appropriate time. And that's not even where it ends. So it keeps going from there. It actually, there's firmware on lots of things. All of the peripherals that you plug into your computer probably have firmware on them. How many people in this room know what option ROM is? Oh, really good. Do I have enough time? I do. I'm going to briefly talk about option ROM. When you plug a PCI-based card into your computer, it comes with a little chunk of firmware with it. And the BIOS knows, because of standards, that it can pull that off and execute that code. So let's say you're a company like Panasonic, and you make network cards. So Panasonic makes these cards, and they put a little, they do all their hardware engineering, right? They spin up a huge amount of money of hardware engineers and layout designers and probably silicon engineers to create this product. They finish spinning it, it validates through all of its tests, and they have someone write some firmware for it because they want to interface more easily. They want to be flexible and be able to update in the field. It turns out today they can with option ROMs. You can put an option ROM on it that ships with the product, and then when you decide, you know what, I actually made some mistakes in there, you can send out what's called a capsule update. And modern UEFI firmware will take that capsule and deploy that new firmware onto the network card. So it doesn't take too much imagination to think, if you were a hacker and you wanted to know the data coming to and from a computer, and you know that there's a little piece of code that runs right before the data leaves and enters the computer, I wonder where I would attack. So I know that companies always use keys and keep those keys secure and never let them leak out of their company, so there's no way anyone could ever fake option ROM and put it onto a piece of hardware. But if that were to happen, this is one of the ways that firmware can be dangerous. But there are lots of ways to mitigate this, and one of the best ways to mitigate this is to understand firmware better. So I'm going to steal a quote from one of my favorite people working in my field, Matthew Garrett. Firmware has actually always been this bad. So don't think of this as a new problem. It's a very old problem. The difference is now it matters. It matters because now you can send out a capsule update to all of your customers, and they can get some piece of firmware that was probably signed correctly and get it loaded onto their hardware. So how do you make a difference? How do you look at this firmware ecosystem that's been built up and do something about it? It turns out that complaining to Intel will help, but the best way to help is to know what firmware you're running. And Intel tries really hard not to write firmware. We write a fair amount of firmware, but there are a lot of firmware vendors out there that are writing the firmware that's running on your hardware. System 76 is a great example of a customer I've been working with that's doing a great job of reforming how firmware works. They're working with us to build a completely open stack. And when I say completely open, I mean from reset all the way through when the OS boots. All of that firmware open source. The idea there is that if I can get that shipping on System 76 laptops, you can then effectively change the firmware running on your computer. And you can understand the whole scope of how it works. So that's really our goal. And getting more companies like System 76 to work with us is the key. Because Intel is just like any other company. We're going to help our customers do whatever it is they want to do. And if they all come to us screaming for open source firmware, we're going to help them do it. So this is the first way you can make a difference. The next, for those of you who haven't heard of the Linux vendor firmware service, hop online and take a look. This is a really interesting thing that started in the past few years. So this is the Linux vendor firmware service. However, there is its equivalent for Windows. Like I was saying, capsule updates are a way to update your firmware. And the Linux vendor firmware service is a way for vendors to say, hey, I want to be able to provide updates in the field. I'd like to register with your service. So you can actually go online and you can see a list of who has signed up for the service and what are they up to. So before I go buy a Dell laptop, I'm going to check and see, hey, do they happen to be sending out updates? Because if they're not sending out updates, and I buy the piece of hardware, there's no guarantee that I'm not running really old firmware. And if the news for the past couple of years has taught us anything in cybersecurity, it's that that's the wrong way to do it. You're really not going to succeed running old firmware. You need to be able to update your firmware. Shameless plug from one of the communities that I work in, ChipSec. ChipSec's a really cool tool. It's written in Python. It can run in the UEFI shell, which we'll discuss briefly. It can also run in Linux and in Windows. It's written in Python, and the idea is it's a way to check the configuration of your firmware. So it's sort of like the first step in defense. If you want to know whether or not a system is vulnerable, whether or not firmware has been tampered with, whether or not the flash part is writable, which it probably shouldn't be while you're running, ChipSec is a tool that you can run and see where your configuration is at, whether or not it meets all of the standards. So basically, ChipSec has a known threat model for a piece of hardware, and will then check to be sure that that threat model has been covered in configuration. I mentioned that it runs in UEFI shell. UEFI is actually just a specification. It is a bunch of companies that got together and said, hey, so we can ship products more effectively, let's standardize how we boot our computers, from Xeons all the way down to Atoms, and all the way down to small ARM processors. So by standardizing that, they've opened the door for open source implementations, and Tiana Core is the current standard open implementation of UEFI. So you're welcome to write your own. Tiana Core is just a great starter point. It's done all the work for you, and it has a community built up around it. So we have a Bugzilla tracking our bugs. EDK2 is the code source. It's actually a combination of source code and a build system all kind of rolled up into one. We started breaking it up so that our build system and most of our core code lives in EDK2, and then EDK2 platforms is where we keep all our platform code. So if you're running, let's say, a ThinkPad, that ThinkPad's platform will have to be in EDK2 platforms for you to be able to build for that machine. And then we're currently working on open source CI. So my goal with open source CI I'm really excited about because I'm trying to work with as many companies as I can. Intel, trying to work with folks from ARM, folks from, I'm trying to work with lots of companies and get all those companies to agree that by doing more CI in the open, we guarantee the firmware is a better product. And I also recently started up community meetings and design meetings to you can actually do the design of your firmware in the open. So if you have an idea before you even implement it, you can come to one of the meetings and see what the people who have been working on this for 20 years have to say. I don't know why that slide is blank. But the next one isn't. So other options. Excuse me. Other options besides Stephano Core. So Stephano Core is a UEFI implementation, but UEFI is not the only way to boot your computer. There are lots of ways to get your computer to boot. One of my favorites is Coreboot. So Coreboot's been around a long time. For those of you who, I think the way I like to describe this, the main difference is UEFI is a way to boot a platform in a very robust way. It has an IP stack. You can actually do HTTPS boot, so you can boot over an HTTPS network. Coreboot is a little more if you just want to initialize the hardware. And I mean if you just want to initialize the RAM. Get to that stage and take it from there. Coreboot's a great option. So Coreboot, for example, can boot and pass off to LinuxBoot. LinuxBoot is a project that essentially pares down Linux small enough so they can fit in the space that you need to boot out of ROM. So you can have a tiny, tiny little Linux install that is the first thing that boots your computer. The beauty here is that it does leverage a lot of already written drivers and code from Linux. So rather than having to trust whatever driver was written by some person, you can use the code that's written already for Linux. I mean, there might be a bug or two in there, because I've heard there are sometimes bugs in the Linux kernel, but it's still a nice way to get involved, and it's a great way to get involved if you've already done kernel programming. For those of you who have looked at the code for EK2, for Stephano Core, you'll notice it looks very, let's say, camel case. Linux boot, on the other hand, is directly from the Linux kernel, so it's a much more natural programming environment for lots of people. The folks at Google are working hard to do lots of stuff in this area, and they've created something called uroot, which is a Go-based file system. I don't know how many people here know what Corutils or BusyBox is? Okay, fair enough. So essentially, if you want to implement basic fundamental applications like LS and RM, these are implemented in Go, and they form a set of tools that let you interact with the file system. Fun story, Coreboot can actually just pass off, instead of to LinuxBoot, to ChipSec. So if you want to do some security research, and you don't want to bother with a very robust bootloader, you can have a very simple bootloader, and then play around with some security analysis. None of this really matters without hardware. So there is some hardware out there that's currently working really well with all this open source software. U-Boot, for those of you who haven't heard of U-Boot, U-Boot is an embedded bootloader. It probably runs on more machines than I can count. And it does run on the BeagleBone Black, and so that's kind of my default standard to go to, but really go look up U-Boot, and it boots on a million things. Coreboot currently works on a lot of ThinkPads. Contact the community to find out what hardware they do run on. They actually have a page that they update with all of their current hardware that works really well. Stephano Core, we're currently working on what hardware we can boot on well. We used to use the Miniboard a lot, but we're starting to mature as a community, and we're starting to pick pieces of software or pieces of hardware that are more open source. So we're trying to find open source hardware that we can boot off of. It's a little bit of a struggle in the x86 world, but we're working on it. Right now we're working off the Up2 board, which is a really interesting board if you have a chance to go take a look at it. It's not open source hardware, but it is really interesting. It's running Atom and Celeron chips. And then they actually just released a Core product too. So for under a few $100, I think it's like $300, you can get a Core processor on one of these boards, which is pretty cool. Let's see. Oh, I'm not sure what I'm explaining later. There we go. Okay, so how do you get involved? Start breaking things. All of these projects have bug trackers. Start trying to get it to work. If you can't get it to work, post in the forums, post on Slack. There's lots of different ways to communicate. If you find bugs, post them to the Bugzillas or whatever programs they use, and start contributing. The great thing about these communities is even over the past year that I've been working in firmware, I've seen these communities grow quite a bit. So it's really exciting to see people getting involved in firmware as they realize it's more accessible. And really that's what this talk is about. It's a really long-winded way to give a high-level overview and say, listen, there's lots of great ways to get involved in open source and in firmware. So with that, I will close out. I will close out, and I think I have a couple minutes, so I will open it up to questions.
How does the management engine play its own?
Yeah. The question was, how does the management engine play in all this? So I tend not to bring the management engine it up unless I have to. No, so the management engine is part of the security features that are available in the x86 world. So a lot of times there's a separate chip for that. There'll be a piece of silicon that does things like the management engine, and TPM is another good example. There's another acronym that I'm forgetting, I'm sure. But those right now, for the most part, are closed source. Management engine being the most famous one. That is a topic of discussion in Intel. We are aware that that's an issue and we need to fix it. There have been lots of great proposals made, and the wheels turn very slow. A big comment. But it is something, it's not only something we're working on, but it's something that we're hoping to release in the future, because we do have solutions. It's just how to release those.
I only bring that up if you secure everything, but you still have that.
Right. Yep. No, it's a great question. Yeah, and please do keep a lookout and keep us accountable. Keep asking. Because as I get asked, I bring that back to my leadership and tell them I'm still being asked.
And is that SMM and STM? Is that what that's referring to?
In a roundabout way, yeah. The management engine is actually its own security feature. So it's a little more than just SMM. SMM is just a level at which you can execute code. And the management engine is kind of its own beast, so to speak. It's actually running Linux. So if that tells you a little bit about how complicated it is, it's not simple. And I don't understand a lot about it, but there are plenty of people on my team that would love to give you resources on how to learn more about that. Any other questions? Okay, well, I'm here for the rest of the evening, so please feel free to step aside and chat with me. I'm happy to go into detail on any of this stuff. And thank you again for coming to my talk.